Hi, I'm Detective Incognito, and I explore events that challenge what we know about our current world. What you're about to hear will change the way you see life. Welcome to another investigation. University of Washington, 2024. David Baker's laboratory produces a protein that has never existed in nature. Not a variation of something natural, not an engineered version of an existing molecule. Something entirely new, designed from scratch by artificial intelligence operating in what researchers call imagination mode. The AI didn't predict what should exist. It invented what could exist. In October 2024, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Chemistry to Baker, along with Damies Hassabis and John Jumper from Google DeepMind, recognizing this transformation from prediction to creation. If you want to understand how machines design molecules that transcend natural evolution, subscribe to this channel, because what scientists achieved suggests AI can explore possibilities beyond what for billion years of biology discovered. This is the story of structures that shouldn't exist according to natural history, yet function perfectly in reality. December 2020, the CASP-1 conference, held via Zoom, became the setting for a moment that would transform structural biology. John Jumper from Google DeepMind presented AlphaFold 2, demonstrating accuracy exceeding 90% in predicting protein structures from amino acid sequences alone. Mohammed Al-Quraishi, computational biologist at Columbia University, later described his reaction candidly. "I was in shock. A lot of people were in denial. The claim seemed impossible. Proteins fold into three-dimensional structures determined by their amino acid sequences, but the number of possible configurations approaches 10 to the 300th power. For 50 years, scientists had struggled to predict these shapes reliably. AlphaFold 2 solved structures in hours with unprecedented accuracy. The impact cascaded rapidly. Google DeepMind released predictions for over 100 million proteins. Essentially every protein science has sequenced. More than 2 million researchers now use the database. The original papers have been cited 32,998 times, making them among the most influential publications in modern biology. But prediction was only the beginning. David Baker at the University of Washington recognized that AlphaFold solved what he termed the forward problem, predicting structure from sequence. His laboratory pursued the inverse problem, designing sequences that would fold into desired structures. The distinction is profound. Prediction asks what will happen. Design asks what could happen. In 2023, Baker's team, in collaboration with MIT, released Diffusion, a generative AI system that creates entirely novel protein structures. Unlike AlphaFold, which predicts shapes of naturally occurring proteins, Diffusion invents proteins that evolution never explored. FrameDiff, another system from the same research groups, produces synthetic proteins independent of any pre-existing biological templates. The comparison is illuminating. AlphaFold resembles predicting the future based on past patterns. Baker's approach resembles writing alternative histories where different outcomes unfold. In May 2024, Google DeepMind released AlphaFold 3, extending capabilities beyond proteins to include DNA, RNA, and small molecule ligands. The system models complex molecular interactions that determine how drugs bind to targets, how genes are regulated, how cellular machinery operates. The technical process operates through diffusion, a method borrowed from image generation AI. The system begins with a cloud of atoms in random positions, then iteratively refines the arrangement until a coherent, functional structure emerges. Björn Wallner at Linköping University captured the significance precisely. The possibilities are endless. Only imagination sets the limits. Researchers suggest this crosses from science into something resembling art. Baker's methods enable what his laboratory calls family-wide hallucination, generating entire categories of proteins with no natural counterparts. The applications span medicine, agriculture, and industrial biotechnology. Designed proteins now serve as vaccine components that bind specifically to viral surfaces. Others function as vehicles for gene delivery. Enzyme design has produced catalysts for reactions nature never evolved to perform. One striking example involves symmetric proteins for gene therapy. Natural proteins rarely exhibit perfect symmetry, but designed structures leverage geometric precision to enhance stability and function. Researchers at MIT's Computer Science and Artificial Intelligence Laboratory emphasize the potential. Better photosynthesis proteins could increase crop yields. More effective antibodies could neutralize resistant pathogens. The paradox is temporal. Evolution required millions of years to explore protein space. AI accomplishes comparable exploration in days. Isomorphic Labs, a company founded by DeepMind's Damies Hassabis, now partners with pharmaceutical firms using AlphaFold 3 for drug discovery, designing molecules that bind disease targets with precision previously unattainable. Yet a philosophical limitation persists. These systems can simulate protein folding, but cannot explain why. Proteins fold as they do. The predictions work without providing mechanistic understanding of the underlying physics. Studies indicate we're designing life faster than we understand it. The true test of computationally designed proteins comes in experimental validation. Baker's laboratory at the University of Washington synthesizes proteins generated by diffusion, testing whether AI imagination translates to physical reality. The success rate is remarkable. Designs that exist only as mathematical abstractions fold into predicted structures. When produced in living cells, practical applications are already emerging. Researchers have designed enzymes that degrade plastics more efficiently than any natural counterpart, proteins that enhance crop resilience to drought and heat stress, therapeutic molecules targeting cancer cells with unprecedented specificity. AlphaFold Server, released as a free resource in November 2024, enables academic researchers worldwide to access these capabilities. The democratization accelerates discovery but intensifies ethical questions. Scientists are designing organisms and molecules never vetted by evolutionary testing. Paul Adams at Lawrence Berkeley National Laboratory offered a nuanced assessment. AlphaFold changed everything and nothing. It predicts structures brilliantly, but doesn't eliminate the need for experimental validation and mechanistic understanding. A fundamental gap remains. Current systems model isolated proteins in idealized conditions. They cannot simulate how proteins behave within the complex, crowded environment of living cells. This remains one of biology's most profound questions. Despite revolutionary capabilities, important constraints persist. AlphaFold 3 achieves roughly 70% accuracy for protein-protein interactions. Powerful but imperfect, the systems struggle with temporal dynamics, predicting static structures, but not how proteins change shape through time. As they perform biological functions, context presents another challenge. Proteins operate within cellular environments containing thousands of molecular species. Current models cannot capture this complexity. The next frontier involves integrating experimental data more tightly with computational predictions. The philosophical question grows more urgent. Is designing without fully understanding safe? Creating molecules that bypass evolutionary testing introduces unknowns. Mohammed Al-Qureshi emphasizes that computational tools haven't replaced experimental biology. They've made it more powerful but not obsolete. Scientists still debate whether this represents discovery or invention. Are these proteins latent possibilities waiting to be found, or genuinely novel creations that wouldn't exist without artificial intelligence? AI doesn't violate physical laws when designing proteins. It explores regions of possibility space that natural selection never visited. The realization is profound. Nature uses a tiny fraction of structurally feasible proteins. Evolution operates under constraints of history, geography, and incremental change. AI liberates design from those constraints, asking not what evolved, but what could exist. The discovery reveals as much about evolution's limits as about AI's capabilities. If artificial systems can rapidly design functional proteins outside biological history, perhaps evolution's path through protein space is just one narrow route among countless alternatives. The Nobel Prize recognition in 2024 acknowledged both prediction and design as complementary breakthroughs. Understanding what exists and imagining what could exist both expand the boundaries of biological possibility. Yet the question persists: if we can design life, should we? The capacity to create molecules faster than we understand their implications demands careful consideration. If AI can imagine structures nature never tried, what does that say about the limits of evolution itself? Perhaps evolution isn't the only author of biological possibility, merely the first one. Understanding this isn't about diminishing natural selection's achievements, but recognizing that the space of functional proteins vastly exceeds what 4 billion years could explore. If studying how artificial intelligence designs molecules that transcend evolutionary history fascinates you, join this journey, because this story teaches us not just about technology, but about the surprising vastness of biological possibility and the unexpected ways intelligence, whether natural or artificial, can illuminate the unwritten chapters of molecular creation. If you liked, subscribe to the channel, like the video, and activate the bell. Leave your opinion in the comments to let me know what you thought. Thanks for sticking around, and see you in the next video.